Hello, and welcome to the Network Profile Summary of the 2020 college football season. I am Major Andrew Dietz, and this profile summary explores the relationship between the football teams in the NCAA Division I football subdivision. Every team has been assigned as its own vertex, and each arc represents a game between those two teams. The first slides in this summary, which cover the introduction and standard terminology, will examine artificially built animated graphs of just the football teams in the Power 5 conferences for easier visibility. However, we will transition to Gephi-based graphics as the material develops and as the graph grows in size with each passing weekend. Let's begin by defining 24 of the most important terms we will encounter. The graph G is defined by two non-empty related sets of vertices and edges. Each vertex or node on the graph represents an object, in our case a specific football team. Each edge or arc is a pair of vertices which represent a connection between those two vertices. Beyond these basic definitions of the graph and its vertices and edges, we can visually represent the graph in any fashion without altering its fundamental composition. Furthermore, any two graphs which share the same set of vertices and the same set of edges are considered equal. Two vertices are considered adjacent if there is an edge whose endpoints are those vertices. We also call these vertices neighbors. Any two vertices are considered connected if there is an unbroken sequence of edges and vertices between them. In this profile summary, we can use connected vertices to analyze common opponents between football teams that are not adjacent themselves. Evaluating the entire graph, we say that the order of the graph is the number of vertices or the length of the set of vertices. Graph G is order 65 since there are 65 vertices on the graph, and the size of the graph is the number of edges. The size of graph G will dynamically grow by the number of games played each week. Next, we will examine components and subgraphs. The graph G before you has four distinct groups of connected vertices which themselves are not connected to each other. You see the red, blue, purple, and green-yellow components. This means that the graph G as a whole is a disconnected graph, and each grouping of connected vertices is called a component. If each colored group represents a football conference, then we can examine types of subgraphs by considering the purple subgraph of Big Ten football teams. Here we see subgraph G5 depicting teams from only one conference. A subgraph is a graph whose sets of vertices and edges are subsets of the parent graphs. Notice that all vertices and edges you see in the subgraph were present in the parent graph G. In this subgraph, we have simulated that every single team in the Big Ten has played every other team in the conference. In this case, where every vertex is adjacent to every other vertex, we call this a complete graph. If we examine this graph and identify a subset of three particular vertices and disregard the others, but retain every edge that existed between the selected vertices, then we have created an induced subgraph. Returning to the complete subgraph, but this time identifying a subset of edges to omit, we create a subgraph of the complete graph whose set of vertices is equal to the complete graph. This is called a spanning subgraph. Finally, every graph or subgraph has a complement, which is the spanning subgraph containing the edges from the complete graph that the original subgraph does not contain. When you combine a graph with its complement, you create a complete graph. For the next set of terms, let us consider the subgraph G4 as the graph of Pac-12 college football teams. In this graph, we can examine the linear connections between vertices. The most basic sequence of connections between two connected vertices is called a walk. In a walk, we can repeat the same edges or vertices, such as in the AG walk depicted here. This example walk encounters 10 different edges and is therefore length 10. A walk in which we do not repeat any edges but can repeat vertices is called a trail. This AG trail is also length 10 and repeats vertex B but does not repeat any edges. A trail which also does not repeat any vertex is a path, such as this AG path. Note, while this is a direct sequence from A to G is only length of 6, an even shorter path is possible. Any path with the shortest possible length between two vertices is called a geodesic, and its length is the distance between the vertices, written as d AG equals 5. A circuit is a closed trail of length 3 or more that starts and ends at the same point, such as this one seen here, which starts and ends at vertex A, but crosses vertex B more than once. A circuit which does not repeat any vertex is a cycle, such as this, also starting and ending at vertex A. However, it does not repeat any single vertex. Focusing on a single vertex J in a connected subgraph G4, we define eccentricity EJ as the distance between J and a vertex farthest from J in G4. It is determined directly by finding the distance between J and every other vertex. Therefore, the eccentricity of J is 4. Furthermore, the eccentricity of the other vertices varies from 4 to 5. The minimum eccentricity among the vertices of G4 is known as the radius, and the maximum eccentricity is its diameter. As a final note, recall that each of the conference graphs we examined are in fact still subgraphs of the larger graph G, and while there is a lot of terminology related to graph theory, I hope this has been helpful in relating some of the more common terms to this network profile summary.